You're told faster than light travel is impossible, that nothing can move through space faster than light, and that's the end of the discussion. But when you take general relativity seriously, the story isn't that simple. The equations allow very strange space-time constructions that seem to bypass the usual limits without directly breaking them. And one of the most extreme proposals is called a Krasnikov tube. In this video, we're going to dig into that idea, see what the math actually says, what kind of energy and technology it would demand, and whether our current understanding of physics truly rules it out or not. You live in a universe with a hard speed limit, and you hit it the moment you start thinking about leaving the solar system. That limit is the speed of light, about 300,000 kilometers per second, around 186,000 miles per second. At that speed, light can wrap around Earth 7.5 times in 1 second, but that number is misleading because your real problem is distance, not speed. Take the nearest star beyond the Sun, Proxima Centauri. It sits about 4.24 light years away. In metric, that's roughly 4 times 10 to the power of 16 meters. In more familiar language, about 25 trillion miles. Light itself needs 4.24 years, measured on Earth clocks, to get there. If you try to go there with any rocket technology that looks even remotely realistic today, you're talking tens of thousands of years for a one-way trip. You launch, a whole civilization rises and falls back home, and only then does your ship arrive. That is the scale you are up against. You might respond, fine, so just go very close to light speed. Build an extreme engine, accelerate harder, and push your starship to, say, 90% of light speed, or 99%, and cut those travel times down. This is where Einstein's special relativity steps in and blocks you. Relativity says that as an ordinary object speeds up, its energy, the energy tied to its motion, climbs in a way that becomes brutal near light speed. At everyday speeds, like a car on a highway or a plane in the sky, you don't notice this at all. But once you start talking about a ship at a significant fraction of light speed, this effect dominates everything. At around 90% of light speed, your ship behaves as if its mass has more than doubled compared to when it was sitting still. Push to 99% and you are dealing with something like 7 times the effective mass. Go even closer to 99.99%, and that factor jumps to around 70. Every extra 9 you add to your speed near light costs you more and more energy for smaller and smaller gains. So let's talk about what that means in hard numbers. Say you want to push a serious interstellar ship about 1,000 tons, that's 1,000,000 kilograms, similar to a tall building's worth of hardware, up to 90% of light speed. Even in a very generous simplified calculation, you are looking at kinetic energy on the order of 10 to the power of 23 joules. To compare, all of human civilization today uses around 10 to the power of 20 joules of energy in a full year. So you are spending hundreds to thousands of years of total global energy use just to accelerate one ship to that speed one time, and you still haven't slowed it down at the destination or accounted for inefficiencies or the mass of your fuel. This is not something you fix with better chemical fuel or a slightly more efficient reactor. This is a fundamental energy wall. Now look at what we have actually flown. Voyager 1, one of the fastest probes ever launched, is moving at about 17 kilometers per second, around 38,000 miles per hour. That sounds fast in everyday terms, but compared to light, it's only about 0.006% of light speed. The Parker Solar Probe, which skims close to the Sun and is currently the fastest object humans have built, gets to roughly 200 kilometers per second at perihelion, about 120 miles per second. That is only about 0.06% of light speed. Not 6%, 0.06. In the language of relativity, those speeds are nowhere near the regime where things get interesting. There is no meaningful time dilation, no major relativistic mass increase, just fast objects crawling across a universe measured in light years. While your technology crawls, cosmology shows you how large the board really is. We see galaxies billions of light years away. We use the way their light is stretched, something called redshift, to measure how fast the universe is expanding and how far they are. The observable universe spans tens of billions of light years in radius. Against that, a few tens or hundreds of kilometers per second is effectively zero. With current engines, your timescales to cross that kind of distance are longer than the age of the universe itself. So put this together. Nearby space on a human map looks friendly. The Moon is about 380,000 kilometers away, roughly 240,000 miles. Mars is tens of millions of kilometers away when it's close, tens of millions of miles. Those are big but manageable numbers. You can cover them in months with rockets we already understand. But the first real step into the galaxy, the jump to the next star, is over 4 light years, about 40 trillion kilometers, 25 trillion miles. At our current top speeds, that means tens of thousands of years. Even if you somehow boost to 10 times faster than our current record, you are still looking at thousands of years. And the physics of relativity is very clear. No matter how much you push, no matter how good your engine gets, you never reach or exceed the speed of light itself. This is the core problem stated directly. The universe is enormous. The nearest star system is more than 4 light years away. The laws of physics, as we currently test them every day in satellites, GPS, and particle accelerators, tell you that trying to reach light speed with a normal ship demands impossible amounts of energy. Real spacecraft right now barely touch a tiny fraction of that limit. So if your plan for interstellar travel is just build faster rockets, you're stuck with journeys that last longer than human history. That leaves one path if you still want to cross those distances in anything like a human lifetime. You stop thinking about speed through space and you start thinking about changing space and time themselves. Instead of trying to outrun light, you look for ways to bend the rules of the game, ways the universe already uses on the largest scales, where whole regions of space seem to separate from each other faster than light could ever travel between them. The key question then becomes, if the universe can already cheat with expansion and other large-scale effects, can an advanced civilization learn to do something similar on purpose on a local engineered scale? That question is what pulls you straight into the idea of faster-than-light travel by hacking space-time itself, not by building a bigger engine. You keep hearing that nothing can go faster than light, so why do cosmologists calmly say that faraway galaxies are receding faster than light right now? That sounds like a contradiction, and this is where the universe quietly shows you how to bend the rules without actually breaking them. On large scales, space itself is stretching. This is not galaxies shooting through a static void like projectiles. This is the distance between galaxy clusters growing because the fabric of space is expanding. When astronomers measure the light from distant galaxies, they see it stretch to redder wavelengths, and from that stretch they can calculate how fast those galaxies are receding from us. The key rule, called Hubble's law, says that the recession speed grows in proportion to distance, so if you double the distance, you double the recession speed. At small distances, this speed is well below the speed of light. But once you get out to tens of billions of light years, the calculation gives you speeds that are greater than light speed. Right now, there are galaxies roughly 14 to 15 billion light years away whose recession speeds, defined by this expansion, are faster than 300,000 kilometers per second, faster than 186,000 miles per second. They are not rockets, they are not engines, nothing is blasting them through space, but the distance between us and them grows so fast that even a light beam we send today will never catch up. From our point of view, they are effectively gone behind a moving horizon. This is not science fiction, this is standard cosmology, supported by redshift measurements from millions of galaxies. This immediately raises another question, which sounds even stranger. How can the observable universe be about 46 billion light years in radius if the universe is only around 13.8 billion years old? Those two numbers look like they should match, or at least be close. If light has had only 13.8 billion years to travel, how can we see things that are now more than 3 times that distance away? The answer is that the number 46 billion light years is not the distance light has actually travelled. It is the current distance to the farthest regions whose light has just managed to reach us after 13.8 billion years, while the space in between has been stretching the whole time. Picture a light beam leaving a distant galaxy when the universe was much smaller. It heads toward us at light speed, but as it travels, the space behind it and ahead of it keeps expanding. By the time that photon finally hits our telescope billions of years later, the galaxy it came from is now around 46 billion light-years away, not 13.8. Space can expand in such a way that the distance between 2 points increases faster than light could cross that distance, without any object locally breaking the speed limit. So, if space can do this slowly over billions of years, did it ever do something even more extreme? According to inflation theory, yes. Early in cosmic history, in a time far less than a second after the Big Bang, many models say the universe went through a phase of extremely rapid expansion. Not just steady stretching, but a runaway phase where the size of the universe doubled again and again in tiny fractions of a second. Regions that were once in contact were pushed so far apart that light could never reconnect them. From the point of view of special relativity, this is not illegal. Because particles are not racing through space faster than light, the geometry of space itself is changing. Locally, if you sit on a small patch of that inflating universe and look at your immediate surroundings, the speed of light is still the limit for anything moving past you. But if you compare two regions far apart, the distance between them can grow faster than a light beam could cover it. Inflation is basically the universe flipping into an extreme expansion mode, using space-time itself as the engine. Now jump to the present day. The universe didn't stop expanding after inflation. Today, observations show that the expansion is actually speeding up again, driven by something we call dark energy. Whatever dark energy is, it behaves like a kind of energy density spread almost uniformly through space, pushing the expansion to accelerate instead of slow down. Roughly 68% of the total energy content of the universe seems to be in this dark energy component. Large surveys like the Dark Energy Survey and missions like Euclid map hundreds of millions of galaxies, and they track how structures grow and how light is bent by gravity to pin down how fast this acceleration is happening. Over very large distances, this acceleration means that more and more galaxies will cross a kind of point of no return, where their recession speed due to expansion becomes faster than light relative to us. In the far future, most of the galaxies we can see today will slip beyond that horizon. Their light will never reach us again. Even though locally, in their own neighbourhoods, physics still looks normal, and nothing ever moves through space faster than light. So here is the key lesson you need to carry forward. The universe already does something that from a distance looks like faster than light separation. It achieves this by changing the geometry of space-time itself, not by building super engines that push matter through space faster than light. Light keeps obeying its local limit, but the space it moves through keeps stretching and warping underneath it. Cosmic expansion, early universe inflation, and dark energy are all versions of this same basic idea, playing out on different timescales and energy scales. Once you understand that, a new question opens up, and it is much more aggressive than anything about conventional rockets. If the universe can use geometry to separate regions faster than light could connect them, can an advanced civilization learn to copy that trick on purpose, but in a controlled, local way? Instead of waiting billions of years for expansion to move galaxies around, can you create your own region of distorted space-time that brings a distant star effectively closer in time without locally breaking the speed of light? That is the point where you leave passive cosmology and step into active engineering of space-time itself. And it is exactly where ideas like warp bubbles, wormholes, and Krasnikov tubes start to turn from abstract math into potential blueprints. So if the universe can stretch space on its own, the next step is obvious and uncomfortable. Can you build a machine that does that on demand and use it as a shortcut? That's where you step into the shortcut zoo people love to talk about. Warp drives, wormholes, all the wild stuff. The key thing you need to keep in mind is this. These are not stories. They are exact solutions of Einstein's equations. On paper, the math says, yes, bus time can be bent into shapes that act like faster than light travel. The problem is not the equations, The problem is the bill. Start with the most famous one, the Alcubierre warp drive. In the mid-1990s, Miguel Alcubierre took Einstein's general relativity and asked a very direct question. Is there a way to move a bubble of space-time itself faster than light, while keeping anything inside that bubble moving slower than light relative to its local surroundings? He found a metric, basically a recipe for space-time where a compact region, the bubble, glides through the universe. In front of the bubble, space is compressed. Behind it, space is stretched. Inside the bubble where your ship sits, space-time is almost flat, practically normal. Your ship just floats there at rest or maybe cruising at some comfortable sublight speed. From the point of view of distant observers, though, the whole bubble can cross interstellar distances faster than a light beam going through normal space. That is crucial because it means the drive doesn't try to push your ship through space faster than light. Instead, it uses the same trick you saw with cosmic expansion. It changes space itself. Locally, light still wins any race inside the bubble. Globally, if you compare where you started and where you end up, you've beaten a photon that had to go the long way through unmodified space-time. On the blackboard, this is perfectly legal. The solution satisfies Einstein's equations. Energy and momentum are accounted for. In a narrow technical sense, it is just as legitimate a space-time as the one describing Earth orbiting the Sun. So what stops you from turning this into engineering? The answer hits in the next step. The energy requirements. The original Alcubierre design, scaled to something that could carry a ship a couple of 100 meters across, needs a kind of energy that normal matter simply doesn't provide. The bubble wall, the thin shell where the space-time distortion is strongest, has to be filled with negative energy density, regions where the energy content is less than the normal zero vacuum, and not just a little. Early estimates show that the magnitude of this negative energy, if you integrated it over the whole shell, would be comparable to or bigger than the total mass energy of the observable universe. On top of that, all of this has to be crammed into a layer of space-time incredibly thin, something like 10 to the minus 32 meters thick, which means a decimal point, 31 zeros, then a 1. That's around 1,000 times larger than the Planck length, the scale where quantum gravity is expected to kick in, but still unimaginably small. So you're being asked to create a shell around your ship, hundreds of meters wide in radius, with a thickness far smaller than an atomic nucleus, loaded with negative energy whose total amount rivals the energy in all the stars and galaxies you can see. That's not expensive in any normal sense. That's basically a red flag from the universe saying, this solution is technically allowed, but you will never pay for it. And even if you somehow did, you'd be operating in a regime where quantum gravity, which we don't fully understand, probably tears the whole thing apart. At this point you might say, fine, warp drives are hopeless. What about wormholes? They show up everywhere in science fiction as tunnels through space-time. You go in one side near Earth, you step out near a distant star. They sound cleaner than dragging a bubble around. Maybe they're easier. But when you look at the details, you hit almost the same problem in a different form. Physicists like Morris Thorne and Yurtsever studied wormhole solutions in general relativity and asked a very specific question. Can a wormhole be kept open long enough for a human or a spaceship to travel through it without collapsing into a black hole or shredding the traveller with extreme tidal forces? The answer was yes, but with a catch. To hold the throat of the wormhole open at a human scale, the stuff threading that throat, the stress energy that acts as the material of the wormhole, has to violate what are called the energy conditions. In simpler language, the region around the throat must contain negative energy density. Ordinary matter, with positive mass and positive energy, won't do the job. So traversable wormholes and warp bubbles, which look like totally different constructions, end up needing the same kind of exotic ingredient. That leads to the next obvious question. Is negative energy even a real thing, or is it just a mathematical trick? Quantum field theory gives you a partial answer. In the quantum picture, even empty space is not truly empty. Fields fluctuate, virtual particles pop in and out of existence, and this gives you a non-zero vacuum energy. Under the right conditions, you can manipulate those fluctuations. The classic example is the Casimir effect. You place two parallel, conducting plates extremely close together, separated by distances on the order of a micrometer, a millionth of a meter. Quantum fluctuations between the plates are restricted in a different way than fluctuations outside, and the result is a tiny imbalance in energy. That imbalance shows up as a small force pulling the plates together. Experiments have measured this force. It corresponds to a region between the plates where the effective energy density is slightly lower than in normal vacuum. That's a real physical case where you can talk about negative energy relative to the ambient vacuum. We're not talking science fiction here, we're talking tabletop physics labs. But there's a brutal scale mismatch. The Casimir force is tiny, roughly thousandths of a Newton per square meter for micrometer gaps. The negative energy region is microscopic. Translating that into what you'd need for a warp bubble or a wormhole throat means scaling up from micrometers to hundreds of meters or more, and from forces you can barely detect to stress energy densities comparable to stars. It's like saying, we can move a grain of sand, therefore we can push a planet. The principle is there, the magnitude is not. So this is where you are. Standard warp bubbles and traversable wormholes are not ruled out by general relativity, but they are so extreme in their requirements that they might as well be impossible for any realistic civilization, at least in the simple forms we've written down so far. You're stuck between a theory that says yes in principle and an energy bill that says you will never build the BESS. If you still want something like for faster than light travel, you need a new angle. You need a setup that doesn't try to wrap your ship in a moving bubble and shove it across the galaxy in one go. You need something that changes space-time in a more targeted, efficient way, where the distortion is laid out along a path instead of around a moving shell. That's the shift in thinking that leads to Sergei Krasnikov's idea, not a flying warp bubble, but a permanent space-time tunnel drawn between two stars. You've seen warp bubbles and wormholes that try to move everything at once, the ship and its own private pocket of space-time. The Krasnikov idea cuts in from a different angle, and it's simple to state, even if it's brutal to implement. You don't move a bubble, you rewrite the space-time along a route. You take the path from Earth to a target star, and you permanently modify that corridor so that, on the way back, ships and signals can beat any light beam that tries to travel through normal space between the same 2 points, all while everything inside the corridor still obeys the local speed of light. The key shift here is timing. You do not get an instant shortcut on the first trip. You pay up front. First, you send a ship from point A, Earth, to point B, the target star, almost the hard way. The ship accelerates to a speed very close to light speed, maybe 99% of it, and it spends years as measured by clocks on Earth crossing those light years. But while it crosses, it's not just coasting, it's working. On board is some future technology, a metric engineering system that continuously changes the space-time behind the ship as it goes. As the ship moves forward, it leaves a modified region behind, a long cylinder stretching from A to B. That cylinder is the Krasnikov tube. It might be several light years long, with a radius big enough for a ship to comfortably fly through, say tens or hundreds of millions of kilometers, but that radius is still tiny compared to the distance between the stars. From the outside, this is just a thin, elongated region of slightly weird space-time running between two systems, like a pipeline or a tunnel embedded in the larger, almost flat galaxy. So what exactly is weird about the space-time inside that tube? This is where the idea gets technical, but you can understand it in plain terms. In relativity, at every point in space-time, there is a set of directions that light can travel into the future. If you drew all those possible future light paths, you'd get something like a cone in a space-time diagram. Anything that moves slower than light has to stay inside that cone. The shape and tilt of that cone depend on the geometry of space-time at that point. Outside the tube, along the normal route from A to B, those light cones point in the usual way. A light beam you send from B to A takes a certain minimum time, measured by clocks at A and B. Inside the tube, the local geometry is adjusted so those cones are tilted in a special way. Locally, for an astronaut riding inside, physics feels basically normal. The speed of light is still the limit. Your ship still follows a trajectory that always stays inside its local light cones. But globally, when you compare departure and arrival times as seen from Earth, the path through the tube lets you get from B back to A in less time than any light ray outside the tube could possibly manage. You can think of it as this: you haven't made your ship break the light barrier at any point. You've changed how future lines up between the two ends of the journey. You've rewired which events in spacetime can connect to which, by subtly rotating the allowed light directions inside the tube compared to outside. The shortcut is hidden in the geometry, not in the engine. Now put some concrete numbers on it and focus on the nearest star that actually matters, Proxima Centauri. The distance is about 4.24 light years, roughly 4 times 10 to the power of 16 meters, or about 25 trillion miles. In the simple picture, your first ship leaves Earth and accelerates to almost the speed of light. From Earth's frame, that trip takes a little over 4 years, say 4.3 years. On the ship, because of time dilation, the crew might only experience something like half a year, depending on the exact speed profile. During the whole outbound leg, the ship's systems are actively modifying the metric behind it, drawing the Krasnikov tube along the route it has just travelled. Once the ship reaches Proxima's system, the tube exists as a permanent structure connecting Proxima and Earth. Now another ship can leave Proxima, enter the tube, and travel back toward Earth at an ordinary sublight speed relative to the tube's interior, maybe again at 99% of light speed measured locally. But because of the way the light cones are tilted in that corridor, the time between departure and arrival as measured by clocks on Earth can be made arbitrarily small in principle. In the math, you can tune the geometry so that for external observers, the return trip seems to take hours, minutes, or even less, while a light ray stuck in unmodified space would still need 4.24 years. Think about what that means. From Earth's point of view, it looks like a ship left Proxima and arrived almost out of order, beating any signal that could have gone the normal way. From the point of view of the travellers inside the tube, nothing illegal happened. Their speed stayed below the local speed of light the entire time. The trick is entirely in how you've bent the global map of space-time between A and B. This is the most important point about Krasnikov tubes. They do not ask you to violate the basic rule that nothing crosses its local light cone boundary. Every world line inside the tube, every path a ship or a signal takes, is time-like, which is a technical way of saying it's always slower than light in the local sense. Special relativity, applied in a small region, never sees a problem. But general relativity, which cares about large-scale geometry, allows you to arrange those small regions so that from the outside the connection between the two ends looks hyper-fast. That's the same loophole that cosmic expansion and warp drives use, but now it's laid down as a fixed line instead of a flying bubble. Instead of dragging a warp pocket across the galaxy with you, you carve out a permanent corridor once and reuse it. It's like upgrading from a one-off, insanely expensive launch to a reusable interstellar subway line. Of course, saying you carve out a tube hides the real difficulty. What does the space-time inside that tube actually look like in detail? How is it stitched to the normal space outside? And what kind of stress energy do you need to hold that structure up without tearing the universe or your ship apart? You've heard the basic story, but now you need to see what this thing actually is in the language of space-time, not just in weird bamboo like tube and shortcut. Because once you see how clean the setup looks on paper, the price tag is going to hit even harder. In the math, a Krasnikov tube is literally carved out as a long cylinder in space-time, running from point A to point B. Think straight line between the stars, but now that line has a real radius, so it becomes a 3-dimensional tunnel. Outside that cylinder, the geometry is basically standard flat space-time, the same kind of geometry you use to describe a quiet region of space far from any big mass. Physicists call that Minkowski space, the default setting when nothing interesting is happening. Inside the cylinder, things change in a very controlled way. The description of space-time, the metric, picks up an extra factor, a function that depends only on how far you are from the central axis of the tube. Call that distance r. at r equals 0. Right along the axis, the function has one value. Further out, it smoothly changes, and by the time you reach the outer edge of the tube, it drops back so that everything matches normal space. That single function controls how much the allowed light directions, the light cones, are tilted along the tube compared to the outside. When you tune that function just right, you get a corridor where signals can cover the A to B distance in much less coordinate time than in the outside region. To keep things organised, people split the space-time into 3 zones. First, there is the outside region. This is everything far from the tube where the metric is basically flat and light behaves exactly as you're used to. If you fire a laser there, the beam moves at light speed and sets the standard for what normal travel from A to B looks like. No shortcuts, no weirdness. Then there is the interior of the tube. This is the main volume you want to use, the hollow region where you will fly your ships and send your signals. Here, space-time is still smooth and locally feels almost flat, but the way time and space are mixed is modified so that future-directed paths between A and B are effectively shortened in coordinate time. When you ride through this interior at any sublight speed, you end up beating a photon that stayed outside every single time. The third zone is the killer, the wall region. This is the thin shell that separates the tube interior from the normal exterior. In this shell, the curvature is concentrated. The function that controls the light cone tilt changes rapidly here, and that rapid change shows up as strong stress energy in Einstein's equations. In simple terms, all the stuff that holds the tube geometry together lives in this thin layer. It's where the exotic properties of the tube are stored, and it's where the physics starts asking for things you don't know how to build. This brings you back to a hard result that doesn't care whether you like it or not. Superluminal effective travel needs negative energy somewhere. Physicists Ken Olam and others studied spacetimes that allow this kind of shortcut, including warp bubbles and Krasnikov tubes, and showed that they all have to violate a basic rule called the weak energy condition. That rule, in plain language, says that if you measure energy density with any physically reasonable observer, you should never see a negative value. Ordinary matter, radiation, dust, stars, planets, all satisfy that. A spacetime that allows faster-than-light connections between distant points cannot obey that rule everywhere. There must be regions where the effective energy density comes out negative. So again, the math is consistent, but it is telling you clearly that there is no free lunch. If you're on a Krasnikov tube, you must create and control negative energy in that wall region. Not briefly, not in a lab setup, but extended over light-year distances and kept stable over long timescales. And it gets worse when you look at thickness. Just like with the Alcubierre warp bubble, you can make the shortcut more powerful by pushing the geometry harder. You can design the tube so the time advantage is extreme. Return trips that are not just a bit faster than light, but overwhelmingly faster when compared to the outside path. The penalty is that the region where the geometry changes has to get thinner and sharper. Some analyses of these spacetimes end up with shell thicknesses down around 10 to the minus 32 meters if you push for huge effective speeds. That is only a little above the Planck length, the scale where we expect quantum gravity to dominate and our current theories to break down. So the wall of your tube becomes a tiny, ultra-thin layer where curvature is enormous, the required stress energy is extreme, and the sign of that energy is negative. You're stacking multiple unknowns on top of each other. How do I generate that energy? How do I shape it into an almost Planck-thin shell? And how do I keep the whole setup stable against quantum effects that we don't fully understand yet? At this point you might ask, alright, if both warp bubbles and tubes need negative energy packed into ultra-thin regions, why focus on tubes at all? Is there any advantage? There is one major conceptual difference. A warp bubble tries to carry your ship and its distorted space-time with you, like a vehicle dragging its own pocket universe across the galaxy. That means all the extreme geometry and negative energy has to move with the craft, like an engine that never turns off. A Krasnikov tube, once it's created, is static in the larger frame. It just sits there, anchored between A and B, like an interstellar highway, carved into the geometry. You pay the cost once on the initial near lightspeed trip when you lay down the tube. After that, any number of ships and signals can reuse the same corridor without you having to rebuild the structure from scratch each time. Energetically, it is still completely beyond anything you can do now, but it comes with the idea of infrastructure instead of one-off stunt. It's closer to building a permanent tunnel under an ocean than launching a single rocket. That changes the way you think about interstellar travel. You're no longer talking about sending rare, heroic missions that barely make it to their destinations. You're talking about a civilization that invests impossible amounts of energy into permanent space-time modifications, then uses them constantly for logistics and communication. The open question is, if you tried to actually build the first of these tubes, what would that mission look like? How do you design a ship that can both survive a near lightspeed trip and rewrite space-time behind it for light years? And what do you really gain the moment that first corridor snaps into place? So if your civilization ever decides to stop just talking about Krasnikov tubes and actually build one, what does that first mission really look like step by step, with real numbers and ugly trade-offs, not just nice diagrams? The story starts with a ship leaving Earth and doing something brutally simple but extremely hard. It accelerates to almost light speed. Say you push it to 99% of light speed, about 0.99 times 300,000 kilometers per second, so roughly 297,000 kilometers every second, around 184,000 miles per second. Proxima Centauri is 4.24 light years away. In Earth's frame, with that cruise speed, the trip takes a bit over 4 years, about 4.3 years. During that entire time, Earth is just watching a dot crawl along, paying the full-time cost. On board the ship, things look different. Because of time dilation, the crew's own clocks run slower compared to Earth's. The relativistic factor here is about 7, which means that for them, the whole journey might feel like around 6 or 7 months. They still need insane amounts of energy to get to that speed in the first place. All the relativity tricks only help with how long the trip feels to them, not with how much energy you had to feed into the engines. Now you hit the next question. During those 4+ years of Earth time, what is the ship actually doing to space-time itself? How does it lay down a tube instead of just flying through empty space like any other probe? The idea is that as the ship travels, some onboard system is active the whole time, continuously modifying the metric in the region it has already passed through. In everyday terms, you have a fill generator that reaches out behind you and slightly rewrites space-time along your trail. By the time the ship has gone a small fraction of a light year, you already have the first stretch of tube drawn. By the time you hit Proxima, you've carved out a full corridor all the way back to the solar system. Picture a straight line from Earth to Proxima, then give that line a real thickness. Maybe you pick a radius of about 1 astronomical unit for comfort. That's roughly 150 million kilometers, or about 93 million miles, the average distance from Earth to the Sun. That gives you plenty of room for navigation errors, orbital motion, and multiple ships. Now take that radius and stretch it over a length of 4 light years, roughly 4 times 10 to the power of 16 meters, or 25 trillion miles. The volume you've edited is roughly pi times the radius squared times the length, which is a number with around 39 zeros in cubic meters. You've literally taken a cylinder of interstellar space that big and given it a different geometric rule set than the rest of the galaxy. Even with small tweaks to the metric, that is a ridiculous chunk of space-time to manipulate. So you arrive in the Proxima system exhausted, with a ship that has burned through star-level energy to reach near light speed, and with a tube now supposedly anchored between the 2 stars. The next question is, when do you actually get the payoff? When does this stop being a painful stunt and become a shortcut? The payoff kicks in only after the tube exists. Once the corridor is in place, you or someone else can use it on the way back. You could have the original ship slow down, maneuver in the Proxima system, then line up with the entrance of the tube and head home. Or you could leave the first ship parked there as an outpost and send a second ship from Proxima that drops straight into the tube entrance. Inside, it travels again at a normal sublight speed relative to the local space-time, maybe 99% of light speed measured by instruments on board and by nearby observers inside the corridor. Because the light cones inside the tube are tilted, the relationship between when you left and when you arrive, as measured on Earth, can be engineered to be dramatically different from the outside universe. Mathematically, you can tune the geometry so that the time gap seen on Earth between departure from Proxima and arrival at Earth can be as small as you like, limited by other physical constraints, not by the raw light's travel time of 4.24 years. In the extreme case, Earth clocks might show the returning ship arriving almost immediately after the moment of the original departure, or even with only a tiny delay, while a photon sent outside the tube at the same departure moment would still be crawling along in normal space, years away. So now you have a tube that turns a 4.24-year communication delay into something that could feel almost instantaneous in the external frame. That leads to the next obvious use case. What if you never send humans again and treat this thing purely as a communication pipeline? Once the tube is stable, you don't have to risk crews on every run. You can fire laser pulses into the corridor, encode data into them, and let them race down the tilted light cones. Those pulses are still limited by the local speed of light inside the tube, but globally they beat any signal sent through ordinary space by years. Instead of waiting 8.5 years for a round-trip message between Earth and Proxima, you could compress that down to minutes or hours, depending on how aggressive the geometry is. Suddenly, a star system 4.24 light-years away stops being a silent, slow pen pal and starts feeling like another city with a delay similar to a long undersea cable. For science, for trade, for coordination between colonies, that's a massive jump. And it happens even if you decide that crewed travel is too expensive and only drones and data use the corridor. But the mind-bending part shows up when you realise that you don't have to stop at one tube. If you can do this once, in principle, you can do it again. You can pick another nearby system, maybe Alpha Centauri A and B, about the same distance, or Barnard's star a bit further out, and repeat the process. Painful first trip, near light speed mission, metric engineering in the wake, and a new fixed shortcut. Over time, your map of local space fills with lines, each line a Krasnikov tube, each line representing an absurd upfront energy cost followed by continuous use. From above, the solar neighbourhood starts to look like a transit map. Earth is a hub connected to Proxima, Alpha Centauri, Barnard Star, TRAPPIST-1, and so on. Then those hubs connect further outward. Information and ships no longer travel according to simple straight-line light travel. They follow this engineered network. You have built not just an interstellar highway, but a kind of galactic subway system, where the tracks are actual regions of bent space-time. The tension is obvious. Every single new tube demands a mission that, by our current standards, is totally impossible. Near light speed travel, exotic negative energy engineering, and accuracy over light-year scales. But once each line is in place, it changes everything connected to it permanently. It's the difference between one ship making a heroic voyage and an entire civilization rewiring how cause and effect, distance and delay actually work between stars. And underneath that shiny picture is a harder question you can't dodge. If you're messing this much with space-time, how much energy are you really talking about? What kind of physical stress are you putting into that wall region? And does any of this survive a serious engineering reality check? If you want to see how hard this really is, you have to look at the raw scale, not just the idea. Once you pick concrete numbers for a Krasnikov tube, the size of what you're trying to control becomes obvious, and it's ugly. Take the corridor we talked about, radius of about 1 astronomical unit, so roughly 150 million kilometers, around 93 million miles, and a length of about 4 light years, about 3.8 times 10 to the power of 16 meters, around 25 trillion miles. Turn that into a cylinder. The cross-sectional area is the radius squared times pi. The radius squared is about 2.25 times 10 to the power of 22 square meters. Multiply by pi, you're at around 7 times 10 to the power of 22 square meters. Now stretch that over 4 light years. Multiply that area by the length, roughly 3.8 times 10 to the power of 16 meters, and you end up with a volume in the ballpark of 2.7 times 10 to the power of 39 cubic meters. That's the amount of space-time you are editing. You're not just tweaking a tiny region near a lab. You're imposing a specific curvature pattern over a volume that large. Even if the distortion per cubic meter is small, the total amount of curvature you need to source sums over that whole region, plus the concentrated wall. Now, what does that mean in energy terms? This is where the estimates get scattered, because different models and choices for the metric give different answers, but they're all bad in the same way. When people integrate the required energy density over the tube's wall and interior, they usually end up with total energy budgets that look like the mass energy of a large planet, a star, or even more. The mass energy of the Sun, E equals mt squared, is about 2 times 10 to the power of 47 joules. That's what you'd get if you could convert the entire mass of the Sun into energy with perfect efficiency. Your current global energy use is around 6 times 10 to the power of 20 joules per year. Even if clever metric designs and more realistic models brought the Krasnikov tube energy cost down by 10, 20 or 30 orders of magnitude compared to the most naive estimates, you're still way beyond anything you can generate now. You're in a regime where energy supply means we have reconfigured our use of entire stars, not we built a better fusion plant. And it's not just the amount of energy that matters, you also have to worry about its sign and its shape. A realistic tube will have regions of positive energy and regions of negative energy. You need both arranged so that they produce exactly the curvature pattern your metric demands. That means stacking layers where energy density is higher than normal vacuum and layers where it is lower than normal vacuum, and doing this in a shell that might be unimaginably thin. Quantum field theory does not let you do whatever you want here. There are results called quantum inequalities that act like rules. They limit how much negative energy you can create, how strong it can be and how long it can last, all tied to the size of the region where you are creating it. These inequalities come from the same underlying physics that gives you the Casimir effect, where you can make a tiny negative energy density between closely spaced plates. They basically say, if you try to generate a lot of negative energy in one place for a long time, you have to pay it back with positive energy elsewhere. You do not get unlimited negative energy for free, so your engineering problem is not just collect star-level power, it's collect star-level power, then use it to sculpt positive and negative energy densities into a shell that might be around 10 to the minus 32 meters thick, wrapping a tube that is 4 light-years long while obeying all the quantum inequality bounds. That is not just hard, that is a level of control over quantum fields that makes current technology look like stone tools. On top of that, there is survival. A Krasnikov tube is not useful if anything that enters it is torn apart. The curvature that gives you the shortcut lives in the metric, and curvature gradients, how fast curvature changes from place to place, show up as tidal forces. The same basic idea explains why strong gravity near a black hole can stretch and compress you. For a tube you can actually use, those tidal forces inside the corridor have to be small enough that a human, a spacecraft hull, and delicate electronics can survive. That means the interior metric needs to be almost flat, with very gentle variations, but the tube still has to do something dramatic overall. That forces you to push the curvature into the wall. The gradients must be tiny inside the tube and huge in the thin shell separating the interior from normal space. You're trying to design a structure where space and time change from normal to heavily modified over a distance that might be close to the Planck scale. Any small mistake in that profile could mean enormous tidal forces in the interior or violent instabilities in the wall. Again, this is an absurd engineering target. It's the space-time equivalent of building a dam where the water level changes from 0 to thousands of meters over the thickness of a sheet of paper, and somehow nothing leaks, cracks, or vibrates itself apart. Except here, the material you are using is the stress energy tensor itself, not concrete or steel. To get a sense of where this sits on the Kardashev scale, think in terms of power. A Dyson sphere around a sun-like star, a hypothetical shell or swarm of collectors that captures most of the star's radiation would give you on the order of 4 times 10 to the power of 26 watts of usable power. That is roughly 10 billion times what humanity uses now. Even with that, if a single tube build demands total energy in the range of 10 to the power of 40 to 10 to the power of 45 joules, you're looking at decades to centuries of full star-level output focused on this one project. Take 10 to the power of 40 joules as a lower bound example. Divide by 4 times 10 to the power of 26 watts, and you get around 10 to the power of 13 seconds, which is a few 100,000 years. Even if you stack multiple stars or find ways to borrow gravitational or rotational energy from compact objects like black holes or neutron stars, the timescales are enormous unless the true energy requirements are much lower than these rough numbers. So in principle, these metrics are legal. Krasnikov tube doesn't violate general relativity, but in practice, to even start thinking about construction, your civilization has to be orders of magnitude beyond a Dyson sphere building species. You need a society that treats stellar power as routine, manipulates quantum fields with fine control on microscopic scales, and can keep huge high-stress space-time structures stable for long periods. From your current position, with chemical rockets and a few small fusion experiments, that gap is almost the main message. The concept of the tube shows you that faster-than-light effective travel is not ruled out by the equations, but it places the bar at a level of energy engineering where interstellar and intergalactic are no longer just distances, they are descriptions of how powerful and stable your control over spacetime has to be. And once you talk about this much power and this much curvature, another problem appears in the background, not just whether you can build a tube, but whether building more than one starts to mess with the cause and effect itself, pushing you from faster travel into time machine territory. How do you build something that lets you outrun light without accidentally building a time machine? That's the nasty question hiding underneath the whole Krasnikov idea, because once you start rewiring space-time, you're not just messing with distances, you're messing with the order of events. Start with the simple claim, which Krasnikov himself argued: a single tube, by itself, can be set up so that it does not create closed time-like curves, the technical name for time loops. In his original work, he showed that if you carefully define the geometry, you can have a ship leave Earth, take the long, near light-speed trip to the distant star, lay down the tube, and then later use that tube to come back hyperfast, all while keeping the causal order consistent. Event A happens before event B, and no signal ever shows up before it was emitted in any reasonable frame that covers the whole process. In practice, that means this: with one tube, you can beat a light beam that stayed in normal space, but you can't send a message to your own past. You can't receive a reply before you send the original message. If you draw the world lines, the paths through space-time, they never form a closed loop where you end up back at an earlier moment in your own history. So one Krasnikov tube looks dangerous but controllable. It's a superluminal shortcut in a global sense, but not a literal time machine. The trouble starts when you realize you can build more than one tube between the same 2 points and give them different time orientations. That's where Alan Everett and others stepped in. They analysed setups with 2 Krasnikov tubes connecting A and B, each one laid down along a different outbound path or at different times, so that when you combine them, you can create a loop in space-time. Here's the rough idea. You use the first tube to get from B back to A too quickly, in the sense that in some external frame you arrive at A before a normal light beam would. Then you have a second tube oriented in a way that lets you go from A back to B, again with a geometry that lets you beat light in the external frame. If the timing and orientations are chosen carefully, the combined path A to B to A can be arranged so that when you complete the loop, you arrive at a time before you started. That path is a closed time-like curve, a loop in space-time where you stay slower than light locally all the way around, but end up in your own past. This is the same category of problem that shows up with certain wormhole configurations and some warp bubble arrangements. Alone, a single shortcut space-time may be fine, but once you start combining them, you can create full-blown causality violations. The math doesn't stop you. General relativity happily writes down a geometry where everything is smooth, the equations are satisfied, and yet you have curves that go back into their own history. Once you have closed time-like curves, all the standard paradoxes are on the table. In principle, you could send a signal from event A, follow a path through one tube, then through the other, and arrive back at event A's location at an earlier time. You could send instructions back that prevent the original signal from being sent. You could create information loops where data appears out of nowhere with no origin, just cycling around the curve forever. The kill your grandfather type paradox is the cartoon version, but even simple cases, like sending a stock price back to yourself, are enough to wreck the normal idea of cause and effect. Physicists take these spacetimes seriously because the equations allow them, but they're deeply uncomfortable with what they imply. They force you to ask whether our usual concept of past causes future is something fundamental, or something that emerges only in spacetimes that don't have these loops. If general relativity on its own allows time machines, maybe the full theory of the universe, including quantum gravity, has to step in and fix that. That's where Hawking's chronology protection conjecture comes in. The idea is not a proven theorem, it's more of a strong suspicion backed by partial calculations, but it goes like this. The universe does not allow the formation of usable closed time-like curves. Every time you try to create a time machine, quantum effects near the would-be time loop diverge, meaning the vacuum energy or stress energy becomes huge, in a way that either destroys the configuration or prevents the loop from fully forming. In simpler language, whenever you bend space-time hard enough and in just the right way to create a time machine, quantum fields freak out. Vacuum fluctuations pile up, energy densities skyrocket, and the nice smooth metric you designed becomes unstable. For wormholes and warp bubbles, semi-classical calculations show that as you tune parameters toward the point where closed time-like curves would appear, the quantum stress energy tends to blow up. The space-time geometry you wanted is no longer a small correction to flat space. It gets swamped by back reaction from the quantum fields living in it. If you apply the same reasoning to Krasnikov tubes, the pattern is ominous. A single tube might be safe in the sense that it doesn't form loops, and might in principle exist as a self-consistent solution. But if you start adding tubes and routing paths in ways that create potential time loops, quantum effects may spike and destroy the configuration, or at least make it violently unstable. In that picture, the universe is protecting chronology, not by banning all superluminal-looking shortcuts, but by brutally punishing any attempt to turn those shortcuts into closed loops in time. So the tension is sharp. One tube could be allowed. It gives you hyperfast travel between two stars, changes communication delays, reshapes interstellar civilization, and yet keeps a global arrow of time intact. Two or more tubes combined in the wrong way push you into time machine territory, and that might be exactly where quantum gravity steps in and says, no further. That means when you talk about building a network of Krasnikov tubes, you're not just planning routes and energy budgets, you're potentially walking a thin line between faster travel and full causal breakdown. You're asking if physics lets you rewrite delay and distance, but still holds a hard line on sending signals to your own past. And that drops you into the next layer of the problem. If quantum effects are the thing that saves causality, what exactly do quantum field theory and semi-classical gravity say about these shortcut spacetimes? How much negative energy can you really have? And do tubes, warp bubbles, and wormholes stay stable when you put real quantum fields into the picture? You've seen that geometry by itself is happy to give you shortcuts, but geometry doesn't get to decide everything. Quantum fields live on top of that geometry, and they come with rules of their own. Those rules act a bit like cosmic lawyers, checking every wild spacetime you write down and asking, okay, but what are you using for stress energy, and does that actually fit the laws of quantum physics? One of the strongest tools in that direction is something called quantum inequalities, worked out by people like Larry Ford and Tom Roman. In plain terms, they say this: yes, a quantum field can have negative energy density in some region, but not as much as you want, not for as long as you want, and not over arbitrarily large distances. If you create a pocket of negative energy, it has to be balanced by positive energy elsewhere, and there are strict trade-offs between the size of the region, the duration and the magnitude. For a warp bubble, a wormhole throat or a Krasnikov tube, that's a serious problem, because all of these ideas lean heavily on having extended regions where the effective energy density is negative or at least very exotic. So any realistic shortcut spacetime has to thread a needle. On one side, you need enough negative energy to bend spacetime into the shape you want, to tilt light cones, to open a shortcut. On the other side, you cannot load up so much negative energy over such a large volume and time that you break the quantum inequalities. If those inequalities are strict and universal, they might rule out macroscopic warp bubbles and tubes entirely, or at least cut their performance down so much that they stop being useful for interstellar travel. Compare what you can actually do in the lab right now with what these shortcuts demand. In Casimir experiments, you put two conducting plates a tiny distance apart, maybe a micrometer, which is a millionth of a meter. Quantum fluctuations between the plates are restricted differently than outside, and you get a small negative energy density between them. That shows up as a modest attractive force. You can measure that force with sensitive equipment, it's real, but you're talking about forces on the order of thousandths of a Newton per square meter over microscopic distances. It's enough to move a tiny mechanical cantilever, not to rearrange galaxies. Scaling that up to an astronomical unit scale shell wrapped around a tube 4 light years long is not just do more of the same. It's like saying, I can create a tiny pressure difference inside a lab vacuum chamber, therefore I can steer a hurricane. The underlying physics might be related, but the leap in magnitude and control is enormous. The Casimir effect proves that nature allows negative energy in small doses. It does not prove that you can turn that into a construction material for these space-time megastructures. On top of that, when people study warp drive spacetimes with quantum fields included, they keep seeing signs of trouble. Semi-classical calculations, where you treat gravity classically but quantum fields realistically, suggest that vacuum fluctuations can pile up in dangerous ways near the edges of a warp bubble. For Alcubierre type drives, analyses indicate that quantum stress energy at the bubble front can grow very large, potentially destabilizing the whole structure. You might get an avalanche of particle creation or wild oscillations in the geometry instead of a clean, stable bubble gliding along. It's reasonable to suspect that Krasnikov tubes would face similar issues, especially near the tube walls where curvature is crammed into a very thin region. That's exactly where quantum fields are most likely to react strongly, because the geometry is changing rapidly over distances near the scales where quantum gravity could become important. In that regime, your carefully designed classical metric might be shredded by quantum back reaction before any ship gets to enjoy the shortcut. That said, theorists don't give up easily, and this is where people start looking for loopholes. Newer warp drive papers try to reduce or even eliminate the need for large negative energy. Some designs use more complicated soliton-like shapes for the warp region, where the energy density is mostly positive, with maybe very small negative regions that are easier to reconcile with quantum inequalities. Others suggest using external gravitational fields like those near black holes or other massive objects to help with the curvature so the engineered part doesn't have to do all the work. Even in those cases, the designs live right on the edge of what semi-classical gravity might allow. They often end up with extremely tight constraints like, yes, this metric exists in principle, but the parameter range where it works is so narrow that any tiny quantum fluctuation kicks it out of the allowed region. So far, nobody has a model that looks both clearly compatible with quantum inequalities and clearly useful for practical FTL-like travel. For your Krasnikov tube, all of this leaves you in a very uncertain place. On the classical side, general relativity says, sure, here's a metric that does what you want, it connects A and B with a hyperfast corridor, and a single tube can avoid time loops. On the quantum side, you have partial evidence that large-scale, long-lived negative energy regions are severely constrained, and that extreme geometries can become unstable once you let quantum fields react to them. The real question becomes, if we ever had a full theory of quantum gravity, not just general relativity plus quantum fields treated separately, but a unified framework, would it still allow extended regions of tilted light cones, like those in a Krasnikov tube, supported by stress energy distributions that do not explode or collapse? Right now we don't know. String theory, loop quantum gravity and other approaches haven't given a clear yes or no here. So when you talk about building a Krasnikov tube, you're really talking about engineering based on a set of maybe conditions. Maybe negative energy can be scaled up. Maybe quantum inequalities have loopholes in curved spacetime. Maybe quantum gravity softens the divergences near tube walls instead of making them worse. Until we know those answers, Krasnikov tubes sit in a grey zone, not forbidden outright, but not clearly allowed either, perched exactly where general relativity and quantum field theory are most likely to clash. And while the theory side fights over that, the universe keeps giving you real, clean evidence that spacetime is not rigid at all, that gravity lends light, that waves ripple through spacetime, that expansion changes distances. If nature already bends and shakes spacetime on huge scales, the next step is to ask, how exactly do we know that? And what does that evidence tell us about what is actually possible to engineer? Before you start talking about engineering spacetime, you need to be sure it actually moves in the real universe, not just in equations. So the first check is simple. Does gravity really bend and stretch spacetime in ways we can see? Or is that just a nice story in textbooks? Look at gravitational lensing. When light from a distant galaxy or quasar passes near a massive object like a galaxy cluster, its path bends. On sky images, you literally see stretched arcs, rings, or multiple copies of the same background galaxy. That's not the light deciding to curve because it feels a force. It's light following straight paths in a curved spacetime. The mass and energy of the cluster warp spacetime around it, and light just follows the geometry. Modern surveys and telescopes like the James Webb Space Telescope and the Euclid mission don't see this once or twice. They see weak lensing signatures from hundreds of thousands of galaxies. By measuring how galaxy shapes are subtly distorted, they reconstruct maps of the dark matter and the large-scale structure of the universe. That's direct, observational proof that mass energy sculpts spacetime, exactly like general relativity says. Then you have gravitational waves, which are even more brutal as evidence. LIGO and Virgo have detected tiny ripples in spacetime caused by merging black holes and neutron stars. Two black holes, each tens of times the mass of the Sun, spiral together and slam into each other. The result is a burst of radiation not just in light, but in space-time itself. Those waves pass through Earth and stretch and squeeze distances by tiny amounts on the order of 1 part in 10 to the power of 21. That's like changing the distance from Earth to the Sun, about 150 million kilometers or 93 million miles, by less than the width of a proton. LIGO's arms, 4 kilometers long, about 2.5 miles, get length changes smaller than a fraction of a proton diameter, and yet the detectors see the signal. You don't get that if spacetime is a rigid stage. You only get it if spacetime is a dynamic medium that can flex, ring, and carry waves. Closer to home, there are tests of more subtle effects like frame dragging. When Earth spins, it doesn't just sit in spacetime, it slightly drags spacetime around with it. Experiments like Gravity Probe B measures tiny changes in the orientation of gyroscopes in Earth orbit, changes that match the predictions of general relativity. Precise tracking of Mercury's orbit and timing of binary pulsars also match the detailed corrections general relativity predicts beyond simple Newtonian gravity. Over and over, the theory that you want to abuse for warp drives and tubes passes every test we throw at it, across different scales and environments. On the largest scales, cosmology gives you a different kind of evidence. We measure how fast the universe expands using several independent methods. Type 1. A supernovae act like standard candles, bright explosions with roughly known intrinsic brightness, letting you estimate distances in megaparsecs, millions of parsecs, where 1 parsec is about 3.26 light-years. Patterns in the distribution of galaxies called baryon acoustic oscillations, give a built-in length scale you can measure. The cosmic microwave background, the radiation left over from the early universe, encodes information about the geometry and expansion history of space-time. Put all of that together, and you get a consistent picture. Space-time is not fixed. The Hubble parameter, which measures the expansion rate, changes over time. Dark energy appears to drive an acceleration of that expansion. Different experiments even disagree slightly about the exact value of the Hubble rate today, creating the so-called H0 tension, which is basically a fight at the few percent level. But none of those disagreements change the core point: space-time evolves. Distances between galaxy clusters grow, structures form and stretch. On scales of billions of light years, space-time is a dynamic, changing object. So when you talk about Krasnikov tubes or warp drives, you are not inventing a new property out of thin air. You're taking the same behavior we already see. Space-time bending around clusters, rippling from black hole mergers, dragging near rotating masses, expanding on cosmological scales, and asking a harder question: what happens if a civilization stops being a passive observer and starts to shape that curvature on purpose? That's the real shift. Right now, you just watch gravity act. You map lensing arcs to infer dark matter. You watch gravitational waves pass through and record them. You track tiny precessions and orbital shifts to confirm the theory. In every case, space-time behaves exactly like the equations of general relativity predict, down to absurd precision. That gives you confidence that if you plug a wild metric like a warp bubble or a Krasnikov tube into those same equations, you're not doing fantasy. You're exploring a genuine, allowed possibility within the same framework that explains GPS, black holes, and the cosmic microwave background. The uncomfortable part is what it implies about your future. If mass and energy can bend space-time, and you already see that happening everywhere in the universe, then in principle, a civilization with enough control over mass energy could treat curvature as a resource, not just a background effect. Then the question stops being, is space-time flexible? Because you already know it is, and becomes, what level of technology does it take to sculpt that flexibility into something like a tube between stars? You're moving from measuring arcs and tiny length changes to planning missions that would deliberately create new curvature patterns. The same equations that explain lensing and waves would become your design tools. And the next step in this story is exactly that. If you wanted to go from seeing space-time flex to actually building the first tube to the nearest star, what would that mission profile look like when you plan it like an engineer, not a storyteller? So how do you actually plan a mission that doesn't just fly to the nearest star, but redraws space-time on the way and leaves a permanent shortcut behind? First, you pick the simplest possible target, Proxima Centauri. Distance about 4.24 light years, roughly 4 times 10 to the power of 16 meters, around 25 trillion miles. With a typical high-end chemical rocket cruising at roughly 50 kilometers per second, about 112,000 miles per hour, you're talking on the order of 25,000 years one way. That's not a mission, that's a geological era. Even if you give yourself a very optimistic fusion drive that can hold you at 10% of light speed, around 30,000 kilometers per second or 18,600 miles per second, you're still looking at about 42 years one way in Earth's frame. That is barely within a human lifetime, and completely useless if your goal is fast back and forth communication. Waiting nearly a century for a round-trip response to a single message is not building a network, it's sending a time capsule. So the baseline you end up with if you're serious about drawing a Krasnikov tube is not fast by rocket standards, it's relativistic. You design a starship that can sustain roughly 1 g of acceleration, about 9.8 meters per second squared, roughly 32 feet per second squared for a long time. You accelerate at 1 g for the first half of the trip, flip the ship and decelerate at 1 g for the second half. In principle, that profile gets you up to around 90% of light speed in a matter of months of ship time. The crew feels Earth-like gravity the whole way due to the acceleration, then due to the deceleration, but that cute description hides a monster. Sustained 1G to relativistic speeds means one of two things. Either you are expelling reaction mass at relativistic exhaust velocities, which demands insane amounts of energy and fuel mass, or you're using something like beamed power, gigawatt to terawatt level lasers or microwaves from a solar system scale infrastructure pushing on a light sail or some other advanced drive. This is not a bigger rocket. This is a ship that is basically a flying fusion or antimatter plant, or a wafer riding on a beam from a megastructure around the sun. The launch system alone is a civilization-level project. On that ship, you don't just pack life support and science instruments, you pack the real payload, the metric engineering system. In today's language, this is science fiction. Arrays of exotic matter generators, quantum field manipulators, or whatever device your future physics gives you that can actually induce the Krasnikov metric. But conceptually, its job is clear. As the ship flies, it continuously modifies the spacetime behind it along a narrow corridor. Every meter you travel, the system updates the geometry in your wake, loading the wall region with the right pattern of positive and negative energy density, smoothing the interior, matching the exterior. You can think of it like a rail-laying train, but the rails here are the tilted light cones along the line from Earth to Proxima. The ship's world line is the survey path, and the generators are hammering in the new geometric structure as you go. By the time you hit the halfway point, half the tube is already there. By the time you decelerate into the Proxima system, the full corridor connecting both stars exists as a real physical spacetime artifact. Now, just flying straight and fast is not enough. Because the tube geometry changes how signals propagate, standard navigation tricks break down. Light doesn't travel the same way inside and outside the corridor, so you can't just triangulate off simple radio beacons and call it a day. You need an external reference frame that stays well defined even as you distort spacetime locally. That pushes you toward timing against very stable astrophysical clocks, like pulsars and distant quasars. Pulsars are neutron stars that spin and emit beams of radiation, giving you extremely regular pulses you can use as timing markers. Quasars and distant galaxies give you fixed points on the sky. Your ship has to constantly compare its onboard clocks and its received signals to this external timing grid, so it knows exactly where it is, not just in three-dimensional space, but in space-time. If you misplace the tube endpoint by even a tiny fraction of a degree over 4.24 light years, you miss Earth's orbit by millions or billions of kilometers, and you end up with a shortcut that connects Proxima to empty interstellar space, near the solar system instead of to your actual home. That's another layer of tension. You're doing extreme metric engineering and precision relativistic navigation at the same time, and any serious error in either one can make the entire mission useless. But suppose you get all of that right. The ship survives the 1G profile, the field generators do their job, the endpoints land correctly in both systems. What do you actually gain the day that tube goes live? Even if you never send another crew, the first payoff is communication. Right now, a light beam from Earth to Proxima needs 4.24 years one way. That means a round-trip message, question and answer, takes about 8.5 years at minimum. With a working Krasnikov corridor, signals sent through the tube can beat that by a huge factor. The exact speed-up depends on how aggressively you've tilted the light cones, but you can imagine compressing that 4.24-year one-way lag down to hours, minutes, maybe even seconds in the external frame. That's the communication version of going from sailboats crossing the Atlantic to fiber-optic cables across oceans. Before the tube, Proxima is a silent outpost, practically disconnected. After the tube, it's a node on your network. You can run continuous telemetry, stream scientific data, coordinate robotic missions, and actually have a conversation where the delay is annoying but tolerable, not life-defining. You transform another star system from a remote science experiment into something closer to a distant city with a long but workable ping time. And that's just with one tube. The moment you see that actually working in your simulations, or in reality if you're far enough along, the next step is obvious and dangerous. If this works once and gives you near instant comms to one star, what happens when you do it 10 times, 100 times, when you start wiring the whole local neighbourhood with these corridors? You get one tube working between Earth and Proxima. The delay drops from years to minutes. So what do you do next? Stop there, or start turning the whole sky into a transit map? The logical move is obvious. You copy the protocol to every nearby system you can reach. After Earth Proxima, you target Alpha, Centauri A and B, roughly the same distance, then Barnard's star at about 6 light-years, TRAPPIST-1 at around 40 light-years, and so on. Each time the pattern is the same, you launch a relativistic survey ship, it accelerates hard, it lays down a tube in its wake, it anchors the far end in the target system. But here's the important shift. Once a new star gets its first tube back to Earth, that star is no longer just a destination, it becomes a hub. From that hub, you can send new missions outward, using that star's own power infrastructure. Proxima can launch its own near-sea ships to other red dwarfs. Alpha Centauri can push tubes to more distant sun-like stars. Within a radius of around 100 light-years, roughly 10 to the power of 18 meters, you have dozens, then hundreds of interesting targets, each one a potential node. The network grows like a spreading front moving through the local bubble, not in straight lines one by one, but in a branching pattern where every new connection accelerates the rate at which you can build more. Now think about what that does to travel times once the network is dense enough. If every tube is tuned so that, from the perspective of the origin system, the return leg of a trip is effectively near instant, then long distances stop being bottlenecks in the way you're used to. Say you've connected a chain of 10 hops, each about 10 light-years long. In normal space, even at 0.1 c, 10% of light speed, that's around 100 years just for the raw travel time, ignoring acceleration and deceleration. In a tube network, you treat it as a series of segments, each one with its own corridor, each one turning a decade of light travel into maybe minutes or hours of coordinate time. In metric terms, you're jumping roughly 10 to the power of 18 meters, about 100 light-years, like it's a long commute rather than a lifetime. You still have to accelerate and decelerate locally. You still have to respect the speed of light inside each corridor, but the way the light cones are tilted in each tube means that globally the distance in time between those far points is drastically compressed. For planning, that transforms how you think about colonization, trade, and even warfare, not in millennia, but in logistical schedules. Of course, every shortcut has a cost, and here the cost is star-scale energy and infrastructure. You'd treat tube construction the way we treat high-speed rail lines or undersea fibre cables, but scaled up unimaginably. Huge upfront investment, then long-term throughput. One tube between two active systems could handle petabits per second of data, streams of high-bandwidth communication, and a continuous line of cargo vehicles running on regular schedules. The more traffic you push through it, the more sense the original energy budget makes. You'd end up with something like interstellar capital projects. Governments, corporations, or whatever your advanced civilization looks like would argue over which links to build first, which stars get priority, what kind of return on investment you expect in science, resources, or strategic advantage. Building a tube to a dead system with nothing interesting might be a waste, but building one to a system with planets, industry, and other outgoing links can pay off for centuries. But as you add more tubes, you're not just doing logistics, you're also doing geometry, and geometry is where the causality hazards show up. Each new tube is a potential new path in space-time. You already saw that even two tubes between the same 2 points, if oriented the wrong way in time, can create closed time-like curves. Now imagine a whole network with loops and branches connecting dozens of stars. Some arrangements of links might be harmless, others might allow you to stitch together a series of tube segments and normal space segments into a time loop. That means you don't just need engineering standards, you need a kind of chronology-safe routing protocol. You'd have to analyze the global geometry of your tube network, not just pairwise links, and rule out any configuration that lets information or ships follow a path that ends before it starts. Some of that might be enforced by physics, if Hawking's chronology protection idea is right and time loop configurations blow themselves up with quantum effects. But you might also need legal or regulatory rules. Something like, you cannot build this link with that orientation, because it would create a causal loop when combined with these existing tubes. So now, your interstellar planning agency doesn't just track traffic and energy budgets, it also tracks spacetime topology. It has to certify that a proposed new tube, with a specific metric and endpoint timing, doesn't push the network over the line into time machine territory. That's a weird place for a civilization to be, passing laws that effectively say, no FTL route this way, it breaks causality for everyone. If tubes like this are even possible in principle, you also have to think about what that means for the Fermi paradox, the question of where is everybody? Maybe you don't see obvious alien megastructures because the key jumping capability isn't just building big things, it's learning to engineer space-time itself. Maybe once a civilization crosses that line, it very quickly wires up its local region with superluminal transit, builds networks like the one we're talking about, and withdraws into those fast channels where we can't easily see them. You'd expect some kind of signature though. A dense network of Krasnikov tubes and similar structures might leave gravitational fingerprints, odd lensing effects, or regions where space-time behaves in ways that don't match what you'd expect from visible matter alone. You might see apparent faster-than-light communication or correlations between distant regions that can't be explained by normal propagation. In that picture, the galaxy could already have private transit networks built by civilizations that are careful to hide them, or we might simply be too primitive to notice the subtle anomalies. All of this is speculation stacked on top of more speculation, but the core point is sharp. The moment you move from one tube to many, you stop talking about isolated science projects and start talking about how an entire galactic civilization organizes movement, energy, and even causality itself. And that pushes you back to the present, because right now you don't have any of this. What you have is theory, a few experiments with Casimir plates, gravitational wave detectors, and some declassified warp drive reports. So the next question is, in the real world today, what are scientists actually doing that connects, even faintly, to all of this talk about warp metrics and Krasnikov tubes? Right now, nobody is building a Krasnikov tube in a lab, but people are quietly poking at the edges of the same physics, trying to see how far general relativity and quantum field theory will bend before they snap. On the theory side, warp drive work has changed a lot from the original Alcubierre idea. In the last decade, researchers have tried to design physical warp metrics, versions that don't need more negative energy than the universe, and don't squeeze everything into Planck-scale shells. Some papers propose soliton-like warp bubbles, stable lumps of space-time that move without changing shape. Others look at configurations where the energy density is everywhere positive, or at least almost all positive, with tiny negative pockets that might fit within quantum inequalities. The pattern that's emerging is this. If you keep the bubble subluminal, slower than light overall, there are metrics that seem to work with only positive energy. The moment you push them into the superluminal regime, all the old problems come back. Huge energy demands, negative energy, and quantum instability. At the same time, this isn't just late-night math for bored grad students. There have been government-backed studies, including reports that later got declassified, looking at things like warp drives, manipulating dark energy, and what extra dimensions would do to gravity. These are not blueprints for engines. They don't end with here's how to build a drive, they're scoping exercises. The goal is to pin down one key question. Does our best physics, general relativity plus quantum field theory, allow any kind of controllable metric engineering even in principle, or do the rules slam that door completely? In other words, are warp drives and tubes physically crazy but allowed, or ruled out at a deep level? Down at the experimental scale, the only real handle you have on negative energy is still the Casimir effect and related quantum tricks. Labs are getting better at measuring and controlling these tiny forces. You've got precision Casimir force setups that can measure forces at the millinewton scale over micrometer gaps. Superconducting circuits that play with vacuum fluctuations and quantum optic systems that squeeze light fields to manipulate their noise and energy distribution. None of this is even remotely warp engineering, but it's all about the same basic ingredient: vacuum energy and its fluctuations. If you ever want to scale negative energy up, this is where the techniques will have to come from. On the cosmology side, big surveys act as constraint engines. Projects like the Dark Energy Survey, Euclid, and deep mapping with JWST give you huge data sets on how galaxies are distributed, how they move, and how their light is bent by gravity. From that, you extract how gravity behaves over billions of light years and billions of years of cosmic history. Any theory that changes gravity in a way that might make warp-like engineering easier has to match that data. So far, the boring model, general relativity plus dark matter plus dark energy, fits extremely well. There are tensions like the disagreement over the exact current expansion rate, but nothing that screams gravity is wildly different in a way that makes Krasnikov tubes easy. So where does that leave the tube idea itself? Krasnikov tubes live mostly in the space of classical GR papers and thought experiments. People write down the metric, analyze its causal structure, check energy conditions, and argue about stability. No experiment is trying to build even a tiny version of a tube, and nobody has a clear path from Casimir plates to a U-size shells. But every new test of GR, every better Casimir measurement, every tightening of quantum inequality bounds, narrows the parameter space where tubes could realistically exist. If future work shows that macroscopic negative energy is impossible, or that any attempt to create extended tilted light cone regions makes quantum fields blow up, then Krasnikov tubes, warp drives, and traversable wormholes all go into the nice mathematics permanently unphysical bin. If instead we find loopholes, maybe in strong gravity regimes, or in some emergent low-energy limit of quantum gravity, then these ideas move from wild to extreme but maybe real. Right now, you're in the middle. You have a theory that happily allows these spacetimes on paper. You have experiments that confirm the same theory everywhere you can test it. You have quantum rules that push back hard against the required negative energies, and you don't yet have the deeper quantum gravity framework that would give a final yes or no. So the real impact isn't that you're about to build a tube, it's that this line of research forces you to rethink what space, what time, and even speed actually mean. Because if you can't treat space-time as a fixed background anymore, if it's something you can, in principle, sculpt, then your whole mental model of motion and distance starts to crack. And that takes you straight into the next step in this story, not another metric or another energy estimate, but the deeper hit. How all of this, warp drives, tubes, inflation, gravitational waves, completely wrecks your everyday intuition about what space and time are supposed to be in the first place. You've spent your whole life thinking of space as a backdrop, like a big empty room with coordinates drawn on it in kilometers or miles. You move through it, you measure distances, you talk about speed, but you treat space and time as fixed. General relativity, and especially things like Krasnikov tubes, hit that picture hard. They say, no, the room is not verbunden or fixed at all. Space and time are part of a physical object, space-time, and that object can bend, stretch, twist, and even be stitched together in ways that change what from here to there actually means. Once you accept that, going from point A to point B stops being just cover the distance faster. It becomes change what that distance is in space-time. Instead of thinking, I'll go faster through space, you start thinking, I'll arrange space and time so that the path I take has less time between departure and arrival, even if I never break the local speed limit. That's what a Krasnikov tube is doing. Light still moves at about 300,000 kilometers per second, roughly 186,000 miles per second locally. Your ship still stays below that inside the tube, but globally, from the perspective of someone watching from far away, the arrival event is much closer in time to the departure event than it would be without the tube. In a Newton-style picture, this is nonsense. In that world, space is flat, fixed, and absolute. Time ticks the same everywhere. If you want a shorter travel time, you only have one knob, your velocity. More thrust, more speed, shorter trip. In the relativistic picture with engineered geometry, you get a second knob, the metric itself. You can change which events are nearby in the four-dimensional sense by changing the geometry. 2 points can be 4 light-years apart in normal space-time, and much closer in a space-time where light cones are tilted along a path between them. You haven't changed the raw number of meters, you've changed the structure that defines how light and matter move between those meters. That's why talking about speed starts to become slippery. If someone at Earth watches you leave Proxima and arrive back almost immediately through a tube, your effective speed looks far above light speed. But every local measurement you make along the way shows you happily cruising below light speed. The shortcut is not hidden in your engine. It's hidden in the way space-time is wired between departure and arrival. You're no longer just an object moving in an arena. You're a user, rewriting the rules of the arena. Then you hit the really uncomfortable part, cause and effect. You saw that one Krasnikov tube designed carefully can let you beat light without generating obvious paradoxes. But add a second tube with a different time orientation, or combine tubes with other relativistic tricks, and suddenly you can get closed time-like curves, loops that allow you to return to your own past. That shift, from fast travel but safe to full-time machine, can come from a small change in global geometry, not from throwing away relativity or doing something obviously illegal. That tells you something deep. The rule no time travel is not written anywhere simple. There's no basic line in the equation saying closed time-like curves are forbidden. Instead, whether you can build a time loop depends on the global shape of space-time, a minor tweak in the network of tubes, a small change in how a warp bubble is arranged, or a particular wormhole configuration can flip you from a causality-respecting universe to one that allows you to send messages to your own past. That suggests that the clean, everyday sense of cause before effect might not be a fundamental law, but an emergent property of spacetimes that happen not to have those loops. This is where Hawking's chronology protection idea becomes more than a catchy phrase. It's basically saying maybe the deeper layers of physics, quantum gravity, vacuum fluctuations, energy conditions, conspire to blow up any configuration that would allow closed time-like curves. If that's true, then no time travel isn't a simple input rule, it's a consequence of the universe violently rejecting any geometry that would break causality. That's a very different way to think about laws of physics. Geometry makes time machines easy on paper. Quantum effects maybe make them impossible in practice. Against that backdrop, metric engineering stops looking like just fancy propulsion and starts looking like the ultimate technology. Nuclear weapons, fusion reactors, antimatter drives. Those are all about rearranging matter and energy inside a mostly fixed space-time. A Krasnikov tube is about rearranging space-time itself. The quantity that matters is not horsepower, thrust, or specific impulse. It's curvature. How much curvature can you generate per meter? How sharply can you change it over distances that might be close to the Planck scale? How precisely can you control those gradients so you don't tear your own ship apart or trigger catastrophic quantum back reaction? If you had a control panel for a mature metric engineering civilization, the dials wouldn't be labelled engine power or fuel remaining. They'd be labelled with things like light cone tilt along corridor, wall curvature profile, allowed tidal force budget. You'd be tuning spacetime the way we tune electromagnetic fields. On the Kardashev scale, that's beyond using a star's energy. It's using that energy to write your own spacetime structure and keep it stored. The mental shift you need to make is probably the biggest part of this story. The real revolution here is not, hey, faster than light might be possible. The real revolution is that once you think in terms of four-dimensional geometry, the whole idea of speed becomes negotiable. Speed is just distance divided by time, when distance and time are fixed. But if the geometry that defines distance and time between two events can be changed, then what you call too far or too slow is no longer absolute. You stop asking only, how fast can I go? And start asking, what does the path between these two events look like in space-time? And can I change that pathy? You're not just trying to outrun a light beam through normal space, You're asking whether you can redraw the connection so that the light beam itself has a different job. That's a huge hit to everyday intuition. It means that the unreachable label on other stars is tied as much to your lack of metric control as it is to any fundamental speed limit. And that leads to the last, sharp question this whole video has been building toward. Given all the theory, the insane energy scales, the quantum roadblocks, and the evidence that space-time really is flexible, where does that leave you? Is a Krasnikov tube something a real civilization could ever ride, or is it a permanent mirage at the edge of our best physics? Right now, the honest answer is harsh. You do not know how to produce negative energy on anything bigger than a microscopic gap between metal plates. You have no full theory of quantum gravity that tells you exactly what happens when curvature and quantum fields both go to extremes. You have no technology that can shape space-time over distances of an astronomical unit, about 150 million kilometers, 93 million miles, let alone over 4 light years, roughly 4 times 10 to the power of 16 meters. Every simple model of a Krasnikov tube or a warp bubble that you can actually write down demands energy budgets that make Dyson spheres look like backyard projects, and quantum inequalities might flat out forbid extended regions of the kind of negative energy you'd need. On any realistic engineering timeline, with current physics and tech, a Krasnikov tube is not hard, it's completely out of reach. But here's the part you cannot ignore. When you take general relativity literally, Krasnikov tubes are not banned. The metric is a valid solution of Einstein's equations. It has well-defined curvature, clear stress energy, and causal structure you can analyze. In that formal sense, it's in the same category as black holes and gravitational waves. Before we saw real black holes and real gravitational waves, they were also just solutions on paper. Superluminal effective travel via geometry is allowed in the same theory that runs your GPS, your satellite navigation, your predictions of planetary motion, and your models of the expanding universe. The math that lets you draw a tube is not a fan-made mod, it's built into the core engine of modern gravity. Cosmology and experiments keep hammering on the same message: space-time is not rigid. Expansion of the universe shows that distances between galaxy clusters change over billions of years. Inflation models show that space-time might have stretched extremely fast in the early universe. Gravitational lensing shows light bending around clusters exactly as if space-time were a flexible medium. Gravitational waves show space-time ringing like a material that can carry ripples. Precision tests with Mercury, pulsars, and Gravity Probe B show that, even near Earth, space-time is slightly twisted and dragged by mass and rotation. Quantum field theory adds its own twist. It says the vacuum is not empty, it has fluctuations, and in special setups like the Casimir effect, you can create pockets where the effective energy density is lower than the surrounding vacuum. That is negative energy in a precise, measurable sense. It's tiny, limited, and highly constrained by quantum inequalities, but it exists. Warp metrics and Krasnikov tubes sit exactly at the intersection of these two insights. Space-time is malleable, and negative energy is real but restricted. They are extreme test cases that ask, if you push those ingredients as far as they can logically go, do you end up with something usable or something that nature refuses to let you build? So where do you fit into this picture? If humanity ever builds anything even remotely like a Krasnikov tube, it will not be because someone suddenly has a clever idea and whips up a drive in a garage. It will be because over centuries you climbed an absurd technology ladder. First you master-controlled fusion, then maybe antimatter production at scale, then star-level energy harvesting with swarms or shells around stars. In parallel, you push quantum field engineering from tiny Casimir setups to macroscopic devices that can dial vacuum energy up and down in bounded regions. On top of that, you crack quantum gravity well enough to know when a curved spacetime is stable, when quantum fields will blow up, and where the safe region of allowed geometries really is. On that path, you get side benefits that are already game changers. If you can manipulate vacuum energy even a little more than now, you get new kinds of propulsion, sensors, maybe even exotic power sources. If you can shape space-time modestly, you can build ultra-precise clocks, compact gravity-based lenses, or defense systems that use curvature instead of armor. If you can harvest a big fraction of a star's output, your energy worries vanish on any human scale, and whole planets can run on what today would look like waste power. The same tools that might one day be used to draw a tube will have already transformed your energy, communication, and computation systems in ways that makes today's technology look like stone tools. By the time a civilization is realistically asking, do we build our first Krasnikov tube, it will already be unrecognizable compared to you. It will be a species that thinks in terms of fields and curvature the way you think in terms of wires and voltage. For them, a tube is not a fantasy jump. It's a high-risk, high-reward infrastructure project at the edge of their capabilities. So when someone says faster than light is impossible, you now know the more precise version. You cannot outrun light through normal, unmodified space by pushing at a normal ship harder and harder, because relativity makes the energy cost explode as you approach 300,000 kilometers per second, 186,000 miles per second. That part is solid. But that's not the end of the story. By reshaping space and time themselves, by changing the geometry instead of just your speed, you open a small in-principle window. A Krasnikov tube is one example of how that window might look. A line drawn across the void that turns a 4.24 light-year gap into something that in coordinate time feels closer than another continent. The laws of physics, as you currently understand them, have not slammed that window shut. They have filled the frame with warning signs, insane energy costs, quantum inequalities, probable instabilities and causality traps, but they have not given a simple, clean, final no. What you have is a conditional of very narrow, not yet, and maybe never, but not obviously forbidden. And for a future interstellar civilization, that not yet is enough. It's the difference between a universe where the stars are permanently out of causal reach and a universe where, if you climb high enough up the ladder of energy and understanding, you might literally redraw the map and make them part of your neighborhood. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.